last talk is such an overwhelming workshop session, and it's been really great. But really appreciate your time here. And what I'm doing, I'm really the spokesperson for work that's been led by my students, especially Yucheng Low and Joey Gonzalez, who are both here, and also Aapo Kyrola and Jay Gu, and my postdoc Danny Bickson, who's also here. And we also involved some collaborations with Joe Hellerstein and Alex Smola. And what I'll talk about today is a little bit about GraphLab, the system we've been building for machine learning over the last a few years, and also the second version that we're in progress right now that addresses natural graphs with large degree nodes. So let's start with the motivation that we're all familiar with. Machines have changed, processes have changed, programming these things is extremely tiresome and hard. So we'll be moving towards higher level abstractions and thinking about how to design this algorithms, especially machine learning algorithms in this context, has been a real challenge for our community, and it's been addressed throughout this workshop. And as we know, MapReduce and Hadoop are good tools, but as the talk from Cloudera talked about, it's good for the kind of feature extraction, first pass over the data. But if you want to do, these are basically data parallel tasks, but if you want to do kind of complex state-of-the-art machine learning algorithms, MapReduce can be highly inefficient. And so what we really want to exploit is the dependency between data. So if you think about matrix factorization, belief propagation, deep belief networks, and so on, we're talking about dependencies between data that's not well captured with MapReduce. And this type of approach, or this type of problem, we call graph parallel problems. And so as an example of graph parallelism, a very simple example that I assume everybody's familiar with, we can think about the PageRank algorithm, where basically I'm estimating the rank of a web page based on an average rank of the web pages that point into me. And the graph here basically is related to the link graph on the web. And so an update in this algorithm will say that if I'm page number 5 here, my page rank is updated to be some relationship, some weighted average of the page ranks of the pages that point into me. And what you do is you iterate this algorithm over the graph again and again until converges. And you can think about this as a prototypical example of what happens in many state-of-the-art machine learning algorithms. You have a dependency graph, which might be a graphical model, it might be the voting dependencies, or all sorts of other dependencies you see in the data. And what we want to do is local updates, where you have an algorithm that looks at my node and neighboring nodes in this data and tries to update my value and perhaps the values on the edges on the neighboring nodes. And what we want to do is apply these algorithms again and again, iterating them over and over again until convergence. When you have an iterative algorithm over sparse data, over graph, then you're covering a lot of machine learning, but it's not well characterized by MapReduce. And because of that, there's been plenty of thoughts about alternatives, especially what's called Pregel, or the public domain implementation Giraph, that try to address this graph parallel problem using what's called bulk synchronous approach, the bulk synchronous parallel model. And the bulk synchronous parallel model is very simple. You have a graph that talks about how your data depends on each other. In parallel over the nodes, you just do some computation totally in parallel, and then you pass messages between the neighboring nodes. So, thanks, Joey. This is his animation. At the end of each iteration, there's a nice barrier that stops everything, and then you go back and iterate. So the bulk synchronous model says, I'm going to iterate everything, and then communicate, and iterate everything, and then communicate. The problem is that bulk synchronous computation can be highly inefficient. And this can come both from a systems perspective and from a machine learning perspective. So let's start with an example of a systems perspective problem with the bulk synchronous model. This is also known as the curse of the slow job, or you can think about it as the curse of the last mapper. So what can happen is you're running a bunch of this process in parallel, but one is really slow, and you have to wait for it until the barrier comes. And then you run in parallel, and another one that's not the same one is slow, and you have to wait until the barrier comes. And then you have to wait. And in the end, your total running time is dictated by the slowest node in every iteration. And this can really slow the practice. This can be really slow in practice. But practical problems are not the only thing that curses this bulk synchronous model. There's also provable inefficiencies when you think about it from a machine learning perspective. So a few years ago, and what motivated us to work on GraphLab, Joey and Yucheng were working on belief propagation, a standard algorithm for graphical models, and they showed a theorem that was actually very well reflected in practice that said that the bulk synchronous model, as you scale the number of CPUs here, in terms of running time, is highly inefficient. This is a theorem when compared to an asynchronous algorithm that works asynchronously over the nodes in the graph. So it works on one node, then another one, then another node, and so on. And if you see in this particular example, which is very typical, one processor implementation of an asynchronous algorithm is faster than an 8-processor implementation of a bulk synchronous algorithm. In this case, it's not Pregel because we didn't have access to Pregel, but it's a very efficient version of it that Joy and Yucheng implemented. And so coming up with an asynchronous algorithm that addressed the belief propagation problem gave us a lot of insight about machine learning, and implementing it in a large cluster was part of the goal of that project. But the little secret here, the sad part, is that implementing this distributed version of belief propagation was very, very painful. It was that long, long, painful process where every week Joy and Yucheng would come to me and say, oh, I spent a whole week on a race condition, and I didn't do any research, sorry. And so that's at least their excuse. And so because of that, we got really motivated about GraphLab because we noticed that there were a lot of problems where bulk synchronous updates like Pregel, Giraph were not so appropriate, and we needed a different framework, a different systems framework that would support the kinds of algorithms that we see on the right here. And this is what I'll talk about today, GraphLab. And GraphLab is really a solution for the kinds of problems we see in machine learning, where you have iterative algorithms over sparse data, where asynchronous computation can give you big gains, and where if you implement your algorithms in terms of GraphLab, we automatically deal with the distribution and parallelization of the underlying systems problem in a race-free execution. So your job as an algorithm designer or user is a lot simpler because you don't have to deal with the systems issue. We have a version implemented in Multicore, distributed setting, and in the cloud setting, and we've been playing with a GPU version of this. So what I'll talk about today at first is a little bit of a kind of overview of what GraphLab is about, and then we'll go into the changes that we have to do with GraphLab to deal with natural graphs and high-degree nodes. So let's start with the GraphLab abstraction. So the GraphLab abstraction is pretty simple. We define a graph, and then we define a lab. No, wait. We define a graph, and that describes the dependencies in your data. We define local update functions or local computations you can perform on this graph. We have a scheduler that you can use to tell us how you want your computation to happen, and you have a consistency model that guarantees race-free executions. So I'll briefly go over each one of these parts. The graph part is the most natural and simplest. You can imagine in a social network, the graph might define social relationships, where data in the data vertex might be my user profile and my current preferences, and data on the edges might be some similarity measure between me and my friends. Now this is a pretty simple thing, very simple representation, and based on it, we can define update functions, which are the core things that you would implement if you write your program into GraphLab. And here's a simple example of an update function in the context of the PageRank algorithm. So I'm looking at a node, and I get to read data from the neighboring nodes and edges. And what I'll do is I'll just write a little PageRank update function that takes in data from my neighbors, updates my rank based on the ranks of their neighbors, and if the rank has changed sufficiently, or the rank of my neighbors is likely to change sufficiently, I go ahead and schedule it, schedule those neighbors. And here's where the dynamic computation comes in. I only schedule nodes as needed. I only schedule computation as needed. And as we'll see from a practical perspective, this can make a huge difference. So to guarantee that this computation, this dynamic computation, happens asynchronously, we have a scheduler for you. And the scheduler is pretty simple. It schedules computations on the processors that we have, whether it's in multicore setting or in the cloud. And those computations are really update functions that run on this graph by looking, for example, at data in A and its neighbor B. And as the computation happens, new vertices get inserted into the scheduler, into some kind of queue. And then the computation continues, and maybe something else gets executed, and new data gets put into the scheduler, and so on. And this process repeats until convergence or until the schedule is empty. Now, you don't have to worry about any of this. GraphLab takes care of that automatically for you. Now, we talked about the three components of the representation, the graph, the update function, and what scheduler you use. The fourth one is a kind of very interesting component that you might think is coming from a systems perspective, but it has quite a big impact on the machine learning problems. And this is the consistency model. And so here's a simple consistency problem that you can have when you write a parallel program. Let's say that I'm executing the red nodes here. So this node can look at its neighboring data and modify it perhaps. This one can look at this neighboring data and modify it. This can look at this neighboring data and modify it. What happens now if at the same time I schedule the center node? If at the same time I schedule this node? What can happen is this too can modify data in the overlapping regions. And if they can modify data, one node might write something while the other node might be trying to read, and you can get into trouble. And this is called a read-write race condition. So this is an example of a race condition you might have. And so often we hear things like, oh, machine learning algorithms are all stochastic, and all these things are just approximate. Who cares about whether you have race conditions or not? And what these people are saying are, forget consistency, because if I ignore consistency, I can have higher throughput. So forget all that. And I might say, sure, forget all that, but for some cases you're okay, but for other cases it can be quite disastrous. So even though you might have higher throughput, you might be doing more updates per second, your updates might be very lousy. So your conversions overall can be quite slow. So here's a simple example. The previous talk talked about matrix factorization. Here's what happens with one particular matrix factorization algorithm, ALS was mentioned in the previous talk, when you allow yourself to have inconsistent updates. When you have run it on 8 processors, this is only 8 processors, and you have inconsistent updates, your training error can oscillate a lot over iterations. While if you use consistent updates, race-free updates, your convergence is very fast to a very nice solution. So this is an example where consistency is really important from a practical perspective. Let me give you a second example here. Here's a little pseudocode of a PageRank algorithm. So I'm going to go over it pretty simply. I take this variable called sum. I define it to be the value of the center node as a reference. I set it to 0. I compute over my neighbors, and then I update that value. Seems like a pretty reasonable program. Let me show you what happens. So if I have consistent updates, you quickly converge and go to the right answer. If you allow yourself to have the program I showed in the previous slide, you go down, and then you get this crazy, crazy, crazy oscillations. Can anybody find a bug in the previous slide? There's a race condition in this problem, and I'll show you the race conditions right here. It is in the sum equals 0. What happens is CPU2 picks up this node and sets its sum equal to 0 and starts writing stuff into it, while CPU1 reads in the particular value while that sum equals to 0 is happening. So the difference between a correct code, incorrect one, is when you do the sum at the beginning, correct one, you do the sum at the end. The difference is very small, it's very subtle, but the impact it can have on the answer is quite significant. And that's why guaranteeing consistency can be a very important thing, even in simple algorithms like PageRank, which you can think about as being very stable and very robust. So the way that you measure consistency, or think about consistency, is by thinking about what's called sequential consistency. If I have this problem here with 3 nodes, what sequential consistency says is, if I execute on CPU 1 green, red, blue, and on CPU 2 I execute blue, green, green, there must exist an equivalent execution on a single processor of green, blue, green, red, green, blue in this example that will give you the same answer as I would have at this point. If you have this, you have sequential consistency. And what Graph guarantees is that this happens. And this can be very important, as I showed you in the previous slides. So as a programmer, you can think about consistency in various ways. For example, the most strict form of consistency we call full consistency, where if I execute the node in the center, I'm not allowed to execute any of its neighboring nodes or do anything to its neighboring nodes. So in this case, it's pretty bad, because if I execute this node, I can't do anything to its neighbor or its neighbor's neighbor. So I can only execute nodes which are 3 hops away or 2 hops away, depends on how you define hops, in parallel. And to address this problem and the fact that often you don't need such a strict consistency, GraphLab offers a range of consistency models. So an example is we offer something we call edge consistency, where we say you can execute this node. You're only allowed to modify data in the edges, but not data in the neighboring nodes. In this case, you can execute nodes which are 1 hop away. And this is safe, where you only read and write to your data and edge data, but you don't only read from neighboring nodes. So as a programmer, you have the ability to tweak what consistency model you have and how it affects your algorithm. Now, this is a quick overview of GraphLab. GraphLab has been quite popular recently, and a number of different algorithms have been implemented within the GraphLab infrastructure. I'm just naming a few here. Many others are out there. And what I'll show you for the next couple minutes is just some results of GraphLab with respect to a couple of these different algorithms. So let's start with the simple PageRank setting. And here I'm comparing GraphLab to Pregel or bulk synchronous updates. And as you increase running time and you measure the error in your PageRank estimation, you see the GraphLab converges significantly faster than Pregel or a bulk synchronous update. And here, Pregel has been implemented via GraphLab, so the systems part of it is pretty similar and is a pretty fair comparison. And to understand why you have such a difference, we can look at the number of updates we're doing per second, and you see that asynchronous setting versus bulk synchronous does significantly fewer updates. And that's why it gets to convergence much faster. Although there's a little bit of overhead when you deal with asynchronous processing, your convergence can be much faster in this setting. And to understand why, you can see that we can histogram the nodes as to how many updates they need to convergence, and 51% of the nodes only need one update before they reach consistency. While a small number of the other nodes, oh, this was a mistake, sorry. A small number of nodes need many more updates. And what GraphLab allows you to do is spend more time with the hard nodes and less time with the easy nodes. Now, this was a demonstration example. Let's talk about a problem that came out of Tom Mitchell's group. So they were using, they're interested in named entity recognition tasks. They want to figure out, for example, that dog is an animal, the word DOG. And the way that they deal with this is they form a bipartite graph which says, the dog appeared with the sentence run quickly, Australia with travel to, Catalina Island with travel to and is pleasant. And by labeling, for example, Australia is a city or a place, then you can propagate it through this graph back and forth and figure out that Catalina Island is also a place. And they wanted to deal with this with a pretty large problem, and they were stuck because it was too hard for them to run on one machine. It had about 2 million vertices and 200 million edges. And because of this, they decided to use Hadoop. So they implemented their system on Hadoop using 95 cores, and it took them 7.5 hours. So they're pretty happy because they were able to solve this problem with Hadoop. Then they learned about GraphLab, and they tried it out on GraphLab, and GraphLab gave them pretty good scaling. So as you increase the number of CPUs, their scaling was actually pretty nice. And this is the multicore version of GraphLab. And with the multicore version of GraphLab, something that took Hadoop with 95 cores, 7.5 hours, took 30 minutes with 16 cores on GraphLab. So that's 6 times fewer CPUs for a 15 times speed up. So they're pretty happy, I think. Now, you can say, Hadoop is a cloud-based system, and GraphLab that I described so far is a multicore version. But we also have a cloud version of GraphLab, which has also addresses many of the cloud setting problems like splitting the data, dealing with communication, and so on. I won't go into a lot of details, but if you look at the same problem here, where Hadoop was taking 7.5 hours on 95 cores, and GraphLab multicore was taking 30 minutes on 16 cores. If you do this on the cloud, with 32 EC2 machines, which is about the same number of cores Hadoop was using, took GraphLab 80 seconds. So that's about 0.3% of the Hadoop time for the same problem. So this independent validation was very exciting for us, and it really motivated a lot of the work. And there's been a lot of other algorithms implemented and validated over GraphLab, getting pretty related speedups over systems like Hadoop. So as another example, we implemented a video cost segmentation problem where you have a video and you want to segment each frame of the video, but you want to say that sky, this segment here in an unsupervised way, is kind of the same as the segment of here later in the video. So kind of segment and label kind of regions. And the way that the implementation worked was an EM kind of algorithm using belief propagation to propagate back and forth beliefs about what segments were. And this was a problem with about 10.5 million nodes, and 31 million edges. And it was a video version of some work that Dhruv was doing. I see Dhruv in the audience. And it's a pretty large problem. And we looked at this in the cloud setting. And so we can think about the speed up of the process. So as we increase the number of nodes we're using, ideally, we're going to get a linear speed up. And what we'll observe is the GraphLab gets a pretty good speed up, pretty linear speed up, although that's not totally perfect, but quite nice. This is kind of the hard or kind of strong scaling property. Another property that's very interesting, especially in industry, it's what's called the weak scaling property. And that property is one where you look at the number of processors and the magnitude of data, and what you do is you double the number of processors and you double the magnitude of data, and you double the number of processors and the magnitude of data. And ideally, you're going to have a nice line here if your algorithm is linear and your scaling is nice in your system. And we see this, the GraphLab has pretty close to that linear line. Basically, we've increased the data size significantly, and we only have about 10% increase in the running time. So it's very nice performance here. And since we're looking at cloud settings where we buy computer time, you can build pretty interesting graphs. So for example, in this one here, we're looking at the cost of solving a particular problem versus running time. This is on Amazon EC2. And what we observe is that in the beginning, adding more machines gives you a lot of performance improvement in terms of running time, but at a little cost difference. But in the end, you have this diminishing returns property where adding more machines doesn't help your running time that much, but costs you quite a bit more. But it's nice to kind of be able to explore this trade-off between computation and cost. So this was a video cost segmentation problem. We also looked quite a lot into matrix factorization problems. In fact, most of our users are using GraphLab for matrix factorization problems today. An example is the Netflix challenge data that was described in the previous talk. And here you're breaking the Netflix matrix into factors over users and d-factors over movies. And what we observe is the GraphLab scaling, this is the ideal scaling, linear scaling, it gets better and better as you add more factors here as the size of d. And that makes a lot of sense because when you increase d, you have more computation per update, and that kind of decreases the overhead of the communication. And the scaling becomes quite nice. And we've also compared GraphLab to other settings, in this case, again, about 2 orders of magnitude faster than Hadoop, and pretty comparable to an MPI version implementation of the same algorithm. So GraphLab is general. This was a problem-specific implementation on API and got pretty comparable performances, which is very rewarding. Now, we talked about dynamic computation, and dynamic computation can really help in some problems. Here, if you just do regular computation where you visit all the nodes, you get this kind of conversions. If you have dynamic computation where you only update nodes as needed, you get faster conversions. And you can do quite a few more evaluations. Again, you can look at running time versus cost. GraphLab being about 2 orders of magnitude faster than Hadoop means you pay about 2 orders of magnitude less to solve your problem than you would pay with Hadoop. And you can explore also the trade-offs of cost versus error. So if you have particular accuracy, you can look at model complexity you'd use and how much you would be paying. Now, in the new version of GraphLab, in addition to the systems properties that I described so far, we're also addressing fault tolerance properties, because in larger problems we can expect some machine failures, and the way we're addressing this is using checkpointing. So every so often we take a snapshot of what's happening, and we have 2 versions of snapshotting, a synchronous version and asynchronous version. And just like in machine learning algorithms, an interesting trade-off between synchronous and asynchronous algorithms here. So an asynchronous algorithm for snapshotting, you say, run GraphLab for a while, stop everything in snapshot, then run GraphLab for a while, stop everything in snapshot, and so on. And if you do this and you look at real data, if you don't do any snapshotting, this is the performance you get. So over time, how many vertices are being updated. So updates until conversions here at the end. And if you do snapshotting this way, synchronously, you have updates, and then there's this lag time when there's a barrier, and we stop to snapshot, and then we continue. But of course, just like in the computation here, we have a curse of slower machine. So if one machine is slower, it's running GraphLab, you have to wait for it before you do your snapshotting, and you can have significant delays. So the example here is, if one machine is delayed by a certain amount of time, for example, 15 seconds, I think here, what you observe is that your whole snapshotting gets delayed, and your whole graph gets shifted to the right. And to address this problem, there's been some classical algorithms. For example, There's the Chandy-Lamport algorithms for asynchronous snapshotting, and it's pretty hard to implement, but thankfully, we can implement our own fault tolerance algorithm as a GraphLab function. So GraphLab fault tolerance is implemented in GraphLab using GraphLab updates. And I won't go through the details, but the nice thing about it is where we had no snapshotting, you had this performance. With synchronous snapshotting, you had the stopping point. With asynchronous snapshotting, it's more smooth, but it's pretty comparable performance. The difference is you don't have the curse of the slower machine. Even with synchronous snapshotting, things slow down when some machine is slow. With asynchronous, we have basically the same performance, which is very nice. So here we're implementing our snapshotting using GraphLab itself. Go ahead. Well, what do you mean by that? Right. The question is the effects of stragglers reduced when you have more machines working on your job? Okay, so if you schedule, the question is, if you schedule the same job on multiple machines, can we get around the straggler problem? And this is a trick that people have used with Hadoop, because there the problems are embarrassingly parallel. You can just break them into dependency problems, and if you solve the subproblem with this machine or that machine is independent. The problem with machine learning is that they're not independent problems. They're connected to each other. So I can't say, I'm going to take out this piece of data and recompute it 5 times, because you're like very interconnected. And what GraphLab is doing is addressing this interconnected setting. So it's a little bit harder to do this kind of replication to address stragglers in the graph parallel setting. Any other questions? So this was an overview of GraphLab. I promised that we're changing the abstraction somewhat. The question is why? If it's so great, why we're doing it? And the reason we're doing it is because we want to deal with natural graphs. And the truth in advertising is that we wanted to solve a web scale graph. There's a nice graph from Alta Vista's web page, kind of crawling graph. And we couldn't solve it with version of GraphLab 1 because there were some nodes that had huge degree. So there was 1% of vertices that had 53% of the edges. And this caused significant problems for the previous version of GraphLab. And that was bad. And I can give you pictorially why this was bad. In the previous version of GraphLab, if I'm executing this node, I look at all its neighbors in the update function. That means I have to lock all of my neighbors. I have to not allow them to do anything, and then process the neighbors sequentially. And this process was extremely slow because some nodes had a ton of edges. 1% of nodes had 3% of the edges. And because of that, we had to rethink the whole GraphLab abstraction in order to address this significant problem. And the problem is not just a problem of locking, it's also a problem of distribution and communication, where it can get very significant. So we haven't talked about how data gets split over the network, but here's a very simple pictorial view. Here's a problem, node Y connected to a number of neighbors. I cut the graph across the network. These nodes go over here, these nodes go over here. When I'm trying to update Y, I have to transmit information about all its neighbors individually across the network. And this transmission can be really slow. And in fact, this was what was really killing us with the large-scale graph. And the issue of high degree, and this issue that was hurting us, is present quite ubiquitously. In social networks, you have some people who are very popular and connected to a lot of others. Netflix, you have some movies which are very popular, and a lot of people have rated them. In all sorts of machine learning problems, for example, template models, you might have some hyperparameters or some shared variables. They're connected to every plate, for example, in this case. And in a model like LDA, you might have a word like Obama that is very common in a ton of documents. And these settings of high degree nodes were very significant and were a big hindrance to GraphLab scaling. And what GraphLab is doing is addressing this problem using 2 changes to its abstraction. They're very simple, yet look very promising and seem to be very successful. The first one is what we call factorized updates. Instead of having a monolithic update where you have a node and we look at all its neighbors at once, we have an update where you look at each neighbor individually and you aggregate their contributions to the update function. And I'll talk a little bit more about that. And the second one is what we call delta updates, where instead of updating a node and all its neighbors at once, we perform local updates, where we only make small changes to the node. And we'll talk about that in more detail next. So factorized and delta updates are the big changes in GraphLab 2. So let's talk about factorized updates in more details. The idea here is pretty simple. I have a node, and I'm going to do an update on it based on its neighbors. What I'm going to assume is that the update function decomposes as follows. A gather phase, where I get to look at node Y and one of its neighbors and perform some computation, and I do it sequentially, and I'm allowed to aggregate those incrementally using a commutative associative aggregation function. So you have to define a gather and some generalized plus operation. And you can imagine, for example, in belief propagation, you're computing the messages for each one of my neighbors, and the plus operation here is multiplying the messages together. Now, once I've computed this update delta, I go and apply it. I change my nodes value. So again, in belief propagation, this might be re-updating my belief. And here, all you have to define is an apply function, how this aggregated updates modify my node. And finally, after I've modified my node, I get to go and tell my neighbor something in a distributed way, using what's called a scatter operation. So simultaneously, I'm able to tell my neighbors something or modify their data in some way. And this is kind of the opposite of the gather. It's a scatter phase. And this is pretty standard constructs in parallel processing. And many of the algorithms that we love and use all the time will fit here. I won't go into a lot of details, but let me just very, very, very briefly tell you that PageRank fits very well in this setting. The gather operation computes how the neighbor's rank affects me. The merge operation, the aggregation, the plus sign, is just summing the contributions from each of my neighbors. The apply just changes my page rank. And the scatter node is the more interesting one. It goes back and says which of my neighbors need to be re-optimized or recomputed. Now, factorized updates can have very, very positive effects. So for example, they can really decrease the amount of communication you have to do. Now, instead of partitioning the graph across the network, as we said before, we partition the graph in a way that the node Y is replicated across machines, and the gather is performed independently on each machine. So this one gathers over here, this one gathers over here, and now you compute a partial solution, F1 and F2, for each one of the machines in the network, and then you merge just those partial solutions. So the amount of communication here is minimal compared to the amount of communication that we had to do before. In particular, it does not depend at all on the degree of Y. And that's the big difference. And since I know how to combine these operations, I just combine them, I obtain the delta, I re-estimate Y, and then I propagate back to the neighbors. And again, the big change here is the communication is independent of the degree, which is very nice. Now, we can think about, if we're doing this, what effect does it have on the consistency model? And here we define a new consistency model we call factorized consistency. And what it allows us to do is run operations on neighboring nodes, which we couldn't do before. Before, no matter what consistency model we couldn't do, we couldn't execute A and B at the same time because they share an edge. Now, we can execute a gather on A and a gather on B in parallel, even though they're neighbors. When we use the apply, it's a little bit more complicated, because if I'm operating apply, if I'm changing the date on A, B can gather on all of its neighbors. It doesn't have to wait on A. Just it can't touch this edge until A is done. So B can do lots of work and modify A just when it's needed. And so the consistency model is a bit relaxed than what we talked about before, but it still guarantees some nice consistency properties and seem to work pretty well in practice. And lots of algorithms can be implemented in this new abstraction. So, for example, I mentioned belief propagation is one. Gather accumulates the messages from neighbors, where we multiply them together. Apply modifies my belief. And scatter computes the potential out messages and schedules wherever neighbors need to be scheduled in the next time step. Perhaps more interestingly, ALS can also be implemented very nicely using this new abstraction. So again, ALS, we have a Netflix matrix, users and movies, and what we're doing is we have a vector WI for a particular user I, we have vector XJ for a particular movie J, And we're updating the weights, for example, W2, based on X2 and X3, because these are the movies that W2 ranked. And the update function is basically some matrix inversion multiplied by some vector. And it might seem unclear how you implement this using the description I said before, but it's actually quite simple. The gather phase estimates this matrix from your neighbor and this vector from your neighbor using just sums of terms. And the apply phase does the matrix inversion locally and multiplies the matrix with the vector. All right, so that was our new abstraction. And one first thing you can do is compare how previous GraphLab, in terms of running time versus error, say, for example, in a PageRank problem, compares to a new abstraction. And we see the factorized updates give you a significant performance boost. So it's significantly faster to use factorized updates than it is to use the previous version of GraphLab. However, factorized updates do have their limitations. So here's an example of a limitation. If I have some modification on the node here that turned red, that gets propagated to its neighbor node, which eventually gets propagated to Y. In the factorized update version, what would happen would be Y would gather information from all of its neighbors together and use it to use the sum of these to update the value of Y. So all of this extra blue work is done when only the red message has changed. So all these blue ones stay the same, all these blue ones stay the same, and only this red one changed. And we're going to do all this extra work. And we can address this using what we call delta updates, which is a very simple observation. We're assuming their operations are commutative associative. So we can just flip them around and redefine this red update as a difference between the old blue update and some delta. So red is blue plus delta. I substitute blue plus delta here. And I change my parentheses and say, whoa, this part over here was the previous cache solution. And all I have to do is apply its delta. So in fact, all I have to do is propagate deltas without ever having to gather off the nodes. And this is going to be a huge change. This delta update is what's going to allow us to deal with the web scale graph in the end. Without delta updates, even with factorized updates, we couldn't deal with the web scale graph. And again, PageRank can be implemented in this setting. I'm not going to talk about details of how it's done. We can compare. This is the graph that we had before. This is a Pregel type implementation. This is GraphLab 1 on PageRank. Running time versus L1 error. If we do factorized updates, we have an improvement. This part is what I showed you a few minutes ago. With delta updates, we get a significant improvement in running time. And that's all because we only touch edges that have changed. Now, we can compare GraphLab 1 to GraphLab 2 in a distributed setting. The results I showed you so far were Multicore. This is over up to 8 machines in a cloud-like setting. And what we'll see is that GraphLab with delta updates is significantly faster than the previous version of GraphLab, which was previously significantly faster, for example, Hadoop. And if you try to understand why this happens, why there's a difference between GraphLab 1 and delta updates, you can think about delta updates as being much smaller, much less communication, and this is exactly what happens. If you look at the total communication we have to do for computation, with GraphLab 2, the scaling over the number of machines of communication is significantly smaller than with the old GraphLab version. And this is where all the gains came in. But as I was building up, our goal was to solve this big problem. This was the AltaVista Web Graph, which was released in 2002, which was released by Yahoo kind of recently. It has 1.4 billion vertices and 6.7 billion edges. And there's been a couple of people have worked with Hadoop on this type of data, including a graph computation overlay on Hadoop called Pegasus, which got about 9,000 seconds to compute on 800 cores. And using GraphLab 2, we can get about 400 seconds on close to half of those cores. And this is a big change and significant value here. And there's since this GraphLab 2 is in infancy so far, there's some overhead that we think we can shave off this value even further. So again, we're getting order plus speed up over Hadoop computation. So just to summarize GraphLab 2 changes, we have decomposable update functions which address high degree nodes. So instead of the previous monolithic updates, we have this gather start update. So this providing us parallelism about the update function. So parallelism with respect to high degree vertices. What data updates do is provide us, expose further asynchrony and provide us with further parallelism even inside the update functions themselves. And these are the two changes in the new GraphLab version. And as we implemented GraphLab 1 and now GraphLab 2, we had significant insights, we feel, about the kinds of problems that in machine learning need to be addressed in parallel. Just a few lessons learned here. Asynchronous computation can be significantly faster than the BSP models, the Pregel-like Giraph models. And I think that's something that we should be really addressing. Dynamic computation can often be faster, but sometimes it's hard to set some of the thresholds when we decide, for example, that some computation does not need to be done. So there's some science to be done that might be even algorithm specific. Consistency can be very important. So not only is it sometimes required for conversions, but often is imperative to get any reasonable results. Of course, there are some problems where consistency is not that important, and GraphLab allows you to tune different consistency models. From the systems perspective, it's of course harder to build an asynchronous system than a bulk synchronous parallel system, but asynchronous systems give you many advantages from a system perspective. For example, the lack of need to barriers as shown by the snapshotting work here. Scaling up an order of magnitude really required us to rethink our representation and rethink our abstractions. And I think we might have to do that in the future, of course, as we deal with larger and larger problems. Now, GraphLab has become pretty popular recently. We've had a ton of downloads from a lot of different companies. About 5 startups are very actively using GraphLab, and I only own one of them. And a number of universities are playing, exploring, or actively using GraphLab. We've had 2,000 plus downloads since we started tracking. And as an example, in this year's KDD Cups, several groups are using GraphLab, and they're overall observing about 2 orders of magnitude speedups over Hadoop, over Mahout, which is a Hadoop implementation. So in summary, GraphLab provides us an abstraction that focuses on the needs of machine learning problems. It makes it easy for you to implement your algorithm, and we deal with the parallelization challenges, the race condition challenges, and all the low-level data partitionings and data management challenges for you. And we can achieve state-of-the-art performances on really large-scale complex machine learning problems rather than simple ones. Today, you can use GraphLab 1, and you can download it from graphlab.org. We're currently working on GraphLab 2, and you can be able to download that hopefully pretty soon. Thank you very much. There's a question back there. Yes.
Really, the edge set is really big, and parallelizing a graph is looking like the adjacent set of every set.
So we don't have to look at all the edges because we have the previous answer. So the delta can be computed by only looking at my edge. I don't have to look at the other edges to compute my delta. But you're right that there is a memory overhead storing the previous values, which I would say is going to be problem specific. I don't think so far we've seen significant problems in terms of memory overhead on this. Of course, if you have a ton of edge data that gets modified at every step, this could be one.
Have you considered algorithms where you wouldn't use all the neighbors, but you would use some random subsample, for example? And if so, it seems like it could use abstraction at the top level that would support that.
Right. So we get asked that question a lot. And with the new version, the GraphLab 1 abstraction was very hard to do that. Now that we have GraphLab 2 with the gather operation, gather could be a stochastic gather. And do some of the things that you're discussing. So the question is, maybe if I have 10 million neighbors, maybe I just look at 1 million of those or something. And this proving something about that would be algorithm specific. But from the systems perspective, I think with the new abstraction, it would be relatively easy to extend it this way.
So in your PageRank example, you showed a small number of nodes and a large number of updates. What if one of those nodes were assigned to a real as well machine? Would that be a problem?
So right now we use randomization in a sense to partition the data, we over-partition the data. So it could be, a slow machine is an interesting thing to think about. GraphLab is more or less designed currently to uniform machines, but nonetheless, just to address your question more specifically, we do split them randomly, and we kind of observe in practice that that's been pretty good to balance slow. However, you can imagine in the future there could be a redistribution step, where as you execute, you discover that there's some part of the graph that requires a lot of attention, and you might want to redistribute it over the network. We haven't addressed that problem so far.
You get a lot of speed up from the dynamic updates. Depending on the threshold, and that changes the correctness.
If you look at my lessons, the lessons learned, I said some of the threshold questions science needs to be done. And I don't know about whether it affects convergence. I would say for most algorithms it affects the error level that you achieve. It's hard to, for all of us, it's hard to say how an epsilon in the node affects the global epsilon of the answer. And this is kind of the question at hand. And we don't have kind of a general theory machine learning for that. But as you know from even approximate nearest neighbors, it's hard to get a global result in general based on kind of local errors that you introduce. For some problems it's possible. Yes?
Is it practical to modify the graph? Like generally you are running this computation on a static graph until it converges. But maybe if you wanted to like compute the algorithm, maybe modify add some edges. Like
right, but no, I hear what you're saying. The question is, would it be practical for the graph to be changing over time? And GraphLab, this is GraphLab 2. One of the goals of GraphLab 3, let's start, is to deal with a setting where you can imagine, think about your Facebook. The social graph is continuously changing over time, and there's lots of new challenges coming there. I think for small modifications of the graph, it would be pretty good with what we have now. But for organically grown graph, we have to do something fancier. We haven't done that yet.
So right now in the version 2, you would like do something that in a batch update, and then you would rerun your algorithm, or
yeah, you could hold it in memory. That you could do some tricks on it, but it wouldn't be like as I said. The really smart thing would be, if I Facebook, the really smart thing would be to load the graph, repartitioning as, Joey joins Facebook, then he has 10 million fans because he's so popular. We have to create a single machine just for Joey. That kind of change is something that would have to be overlaid. But, okay.
So I thought the asynchronous checkpoints and the update function that was really cute was around model. Does GraphLab provide ways to sort of compose together two orthogonal update function? Or when I happen to say change in the PageRank implementation of the implementation?
You can have multiple update functors. So update functions are really functors, they have state as well. And your code can have multiple of them, and your scheduler can decide how they get started.
Data flow aspects, which I would say do one kind of update function first, then change
another. We can do that. Yes. Okay, I think this is the hint that we need to stop. Thanks so much for